In this video, we're going to discuss significance tests of the coefficients in the model, meaning the intercept and the slope. The real question in one of these significance tests is this coefficient actually contributing to the model? Is the intercept doing anything, or is it actually equal to 0? Is the slope doing anything, or is it actually equal to 0? So this is the model that we've proposed as representing the line of best fit through the data. So we have y measurements and x measurements, and then we're going to estimate the intercept and slope. And we know that there will be some error. There's going to be some mistakes present in our creation of this line because we can't possibly represent every data point in the set. So a specific example of this is using oversized packages in the warehouse to make predictions of how long it's going to take to deliver those packages. So there will be some intercept and some slope that will help us create the line of best fit. Now we're assuming that a line is actually a good model for the data, and we don't know that that's true. If either the intercept B0 or the slope B1 is likely to be 0, then the model isn't exactly what we expected. Looking back up here at this equation, if B1 is actually determined to be 0, then the model is y equals B0 plus 0 plus some error. So y is actually equal to some number that we estimate. Then it wouldn't actually change with oversized packages, and our prediction will always be the same. If B0 is estimated to be 0, well, then we still have this B1 times x term that will show us how the hours per driver change as oversized packages change. But it's possible that either the slope or intercept or both are determined that, they're really not that different from 0. For hypothesis tests of the significance of each coefficient, we're going to need the same things that we needed for any other hypothesis test. We need a hypothesis, a test statistic, and the distribution of that test statistic when the null hypothesis is true. These are all the same tools we've needed before. We needed to know, are we testing to see if something is equal to 6? Are we testing to see if two things are equal to each other? We need to know what quantity we're going to calculate in order to do that test. And then we needed to know something distributional about that quantity. So the first thing we need is a null hypothesis. And for every hypothesis test that we do in this class, we'll be testing to see whether the coefficient or the intercept or slope is equal to 0. So coefficient is just a word that I use to mean all of the intercepts and all of the slopes that we study. So the null hypothesis is going to be that this thing we're interested in right now is equal to 0. The alternative will be that it's not equal to 0. And we know that alternative hypotheses can have greater than or less than in them, but for this class, since we're using R, which is a statistical programming language, it doesn't have intuition about greater than or less than. So it's always going to naturally perform the default test not equal. And then you can make judgments about greater than and less than. So these will always be our null and alternative hypotheses. We just want to know, is this value significant? Is it meaningful? Does it contribute to the model? Or is it actually 0 and we should just take it out? So if the null hypothesis is true, then it means, hey, this intercept or this slope is actually 0. So just take it out of the model. So when we find that something's not significant, we should remove it from the model. We do the same test for B1. So the null hypothesis would be that the slope B1 is equal to 0, and the alternative would be that it is not equal to 0. So far, we've said absolutely nothing about the distribution of x or y or the errors, nothing about the model. We've used the method of minimizing the squared errors, which is called ordinary least squares, and it doesn't require distributional assumptions. So the way we minimized the squared errors, the distances between the dots and the line, all of that is valid no matter what the distributions are. So we can always come up with estimates. The hard part is testing whether those estimates are actually statistically significant. So in order to do those statistical significance tests, we have to assume that the errors are normally distributed with a mean of 0. And that's something that we're going to come back to later on, testing to see whether the errors are actually normally distributed. Now, a result of that assumption is that we're assuming that y is normally distributed. So we need our thing that we're trying to predict, our response, to have a normal distribution. But let's go back a step. What actually are B0 and B1? What are the slope and the intercept in this model? We always create the model based on sample X and Y. So you have this sample of data in an Excel spreadsheet, and you're creating the best line through those points. If we used a data set from 2011 and 2012 instead of the data set from 2013 and 2014, would we find exactly the same measures of oversized packages and exactly the same measures of hours that it took to deliver them? Probably not, because those years are different. Maybe the drivers were even different in 2011 than they were in 2013. So we have to think about how there's going to be some natural variation that would be very typical. So if we would create a new model for 2013 and 14 that was different from the model we created in 2011 and 12, we would expect B0 and B1 to be different. Even if they're just slightly different, they're probably going to be different. So the point of this is that B0 and B1 are actually random variables. They can change, and they're functions of X and Y. So if you change X or change Y or change both of those things, then you're going to be changing the slope and intercept. Even if it's just the tiniest tilt of the slope changes, then you're still having a change. So the intercept and the slope are allowed to vary. And for that reason, we need to know, is our estimate of them a natural variation, or is it a significant variation? So let's talk about the test statistic for our model. We're going to assume that B0 and B1 are normal. And this is going to be true based on the other assumptions we've made. We assume that the errors are normal with an average of 0. And we, as a result, are assuming that Y is normal. So for large samples, B0 and B1 are going to be normal enough that we can do significance tests with a normal distribution. And we're going to use a t-test to test their significance. The test statistic is written here. T equals our estimate for B0 minus 0 over the standard error for B0. Now, this is the variation that's explained by the model on top. That means the model creates this estimate of the intercept, and we're going to compare that to 0. If the difference between the estimate and 0 is large, meaning if the estimate is large, then we have something substantial. But how do we tell if something is substantial? Remember the concept of signal to noise in the hypothesis tests video. The standard error for B0 is the noise. The signal is how large B0 is, and the error around it is the noise. So if we create this estimate, and we say the estimate of B0 is 6, well, is 6 a big or a small number? If you're talking about how many dollars that you made in a year, 6 is a relatively small number. But if you're talking about how many cars you own, 6 is a relatively big number. So that standard error in the denominator is what is giving us context about 6. It's going to tell us whether 6 is big or small based on how big or small that standard error is. So if I have the number 6 and I say, but it might move around 1 or 2 units. Well, 1 or 2 units is not a lot compared to 6. But if I say it might move around 1 or 2,000 units, then 6 is really small. So this is just telling us how close to 0 6 actually is based on how much B0 might move around. And we're going to say, these are all the things I just said. We're going to say that this thing has a t distribution with n-1 degrees of freedom, where n is the sample size. Now let's look at the R output. We talked about the R output in the last video. We said that we first see a reporting of our model, an error summary, a coefficient summary, and a model fit summary. So let's talk about in detail what we get out of the coefficient section. First, a reminder of what our model looks like. We're predicting average hours per driver using % oversized packages. The estimated coefficients for the model are here. They are the first two numbers in that coefficient section. The estimate of the intercept is 4.9, and the estimate of the slope is 26.6. So if we were going to write out the model, we would want to write it out such that we are predicting hours per driver with an intercept of 4.9 plus 26.6 times % oversized packages. Now, % oversized packages is an actual percent. So if it's 2%, it's 0.02. If we were trying to make a prediction of how long it would take to deliver all of the packages for the day, if 2% of them are oversized, we would multiply 0.02 times 26.6 and add 4.9 to get the total predicted hours per driver. So that's our proposed equation. But we need to back up one step. We need to test to see if 4.9 is actually a good estimate or if we should better use 0. And we need to do the same thing with 26.6. Is it a good estimate or would we be better to use 0? So let's look at the other details of these estimates that are provided. Look here at the t-value. What's happening in this box is that the test statistic is constructed for us. Here we have the estimate, and here we have the standard error. And when we put 4.9 over 0.1168, we get a value of 41.98. That's the value of the test statistic. When we put 26.6 over 1.8677, we get 14.25. So R is calculating the estimate of the coefficient, it's calculating a standard error, and it's also providing a test statistic value. So we can start to do our hypothesis test. So let's do that hypothesis test now so that we can envision what's happening under the surface. First, we have to specify alpha, the significance level of the test. And let's say that that's going to be 0.05. That would mean I'm allowing a 5% chance of making a mistake. Now let's identify the critical region associated with alpha and whether this is going to be a one-sided or two-sided test. Now, I've already told you R always uses a two-sided test because it doesn't know if you want to test greater than or less than. This is relatively standard. You could do your own testing if there's some very subtle effect that you're not seeing with the two-sided test. So here's our normal distribution. First, we already know the significance level of the test, so we're going to identify the critical region. We're going to put half of our significance level on either side because this is a two-sided test. So let's divide our error into two parts. We'll put alpha over 2, which is 2.5% over here, and 2.5% over here. And now we need to identify what value is marked off by that percent of the area under the curve. That would be 1.96 and negative 1.96. This number should sound familiar to you. Now, when we do our hypothesis test, our t-values were way over here on the line. So were they above 1.96? Absolutely. They're definitely in the shaded region, even though the shaded region is so tiny over here that we can't see it. These values are well beyond the marker for the critical region. They're definitely not in here. They're not between negative 1.96 and positive 1.96. So these values are going to be so far from 0 that we can confidently reject the idea that they could ever be equal to 0. So if they were maybe 0.4 or negative 0.8, we might say, oh, those are safely within the not critical region. So we're going to just accept the null hypothesis that those are 0. But they're not. They're way outside of that region. They're well beyond our confidence barrier of 1.96. And we can say this is enough evidence to reject the null hypothesis that these are equal to 0. So the test statistic lies well within the critical region for each of these tests, for both the intercept and the slope. So we're going to reject the null hypothesis and accept that both b0 and b1, the intercept and the slope, are very significant parts of this model. Let's go back to the R output now. We saw the estimates, the standard errors, and the t-values, and now we know how useful those are. But let's look at these p-values quickly. This is actually the p-value of the two-sided test. So for the intercept, the p-value is less than 0.000000 and so on, 2. So this is a tiny, tiny, tiny number. The p-value is very small. It means this is the chance that we're actually making a mistake and we're wrong, that when we say it's not equal to 0, that it is equal to 0. So this is such a small chance that we can say confidently, we know that the estimate is not 0. It's really going to be 4.9. We're going to take 4.9 to be a good estimate of the intercept. And the same is true, looking at this p-value, for our slope. We can say 26.6, we're very confident that that should not be a 0, that it is actually a substantial value that contributes to the model. Now, looking at the stars on the outside of these p-values, this is sort of the quick and dirty way of doing a test. This is just a cheater star test over here. The 3 stars, according to this key down here, and the key will always be the same, but according to that, it says, hey, your 3 stars mean that your p-value is between 0 and 0.001. And according to the hypothesis test rules, if our p-value is less than 0.05, then we pass the test. We reject the null hypothesis and accept the alternative. So let's see. If we have 3 stars, then we should know right away, reject the null hypothesis that this coefficient is equal to 0. And the same is true if we have 2 stars. It means it's between 0.001 and 0.01. And all we want is that it's less than 0.05. So even if we had 2 stars, we could reject the null hypothesis. And looking at the 1 star, it means between 0.01 and 0.05, which is still less than 0.05. So 1, 2, or 3 stars gives us license to reject the null hypothesis and accept these estimates as good estimates of the slope and intercept for the model. So these are the p-values for the test. They're very small in this case because those test statistics were so large. And the stars indicate the level of significance for which we can reject the null hypothesis. So they tell us right away that we have a significant intercept and slope and we can accept these estimates. Using R for linear regression requires very, very little work on the part of the researcher. It's the interpretation that's a big responsibility. R is calculating the line of best fit. It's even doing the significance tests for us. Our responsibility is more in the interpretation, and that's really the hard part.